Today I'll be covering Pythagorean Theorem. So for today's agenda, we're gonna learn what it does, and then we're gonna learn how to use it with some examples. So let's begin. Pythagorean Theorem. In a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So what exactly does this mean? Well, I have a picture here, and this picture is gonna help us unpackage this sentence. So let's reread it again. So here it says, in a right-angled triangle. So we have a triangle for sure, but how do we know if it's a right-angled triangle? Because if we don't have a right-angled triangle, then we have no hopes of trying to use Pythagorean theorem. So here's how we know. One thing we have to look for is this small little square, because the small square inside a shape informs the reader that the angle is 90 degrees. So as long as we have this, we know that, hey, we're in good hands and we can use Pythagorean theorem. The second part reads, the square of the hypotenuse is equal to the sum of the squares of the other two sides. In order for me to explain this, I'm going to introduce three variables, A, B, and C. Now, a triangle has three sides, and the side that is opposite of your 90-degree angle, this side is always going to be called the hypotenuse. Hypotenuse. And I'm going to denote it by the variable C. So the hypotenuse is called C. The other two sides of the triangle, they are called legs. And the legs, I'm going to denote them by the variables A and B. And it doesn't matter which one's A or which one's B. However, C does matter. C is always your hypotenuse. Now that I've labeled the triangle, I can properly translate this sentence. The square of the hypotenuse is equal to the sum of the squares of the other two sides by using algebra. And this is incredibly famous, very well known. You probably learned it in middle school. It's a formula that goes by a squared plus b squared equals c squared. So again, the sentence or the part that I highlighted in red, basically all it's saying is that when you take the length of the legs and you add the squares of them, they're going to equal the length of the hypotenuse square. Summing it all up, here we have the definition in English, and we were able to unpackage the definition and show it as a visual. And once we established all the terminology associated to this triangle, we were able to translate this into algebra, and we get this super famous equation, a squared plus b squared equals c squared. And this is what we will be using in our algebra class in order to find the missing side of a right-angled triangle. So let's go ahead and look at some examples, and I'll show you how we will apply this in our class. But before we actually get into the examples, these are just some things to keep in mind. So these are conventions that are used. The first one being that the side that's across the 90-degree angle, this one right here, this side will always get labeled as C. Okay, your hypotenuse is always going to be C. And the other two sides, they're called the legs. And these ones, it does not matter which one gets labeled as A, which one gets labeled as B. Now we have to follow these conventions if we want to properly execute this definition here, or this equation. All right, here we're under the assumption that we will always be labeling the hypotenuse as C. All right, now that that's out of the way, let's dig into the examples. Let's begin by looking at this problem here. So example, two sides are given. Use Pythagorean theorem to solve for the third side. So what Pythagorean theorem promises is that as long as you know two of the sides, if you use the formula a squared plus b squared equals c squared, you will be able to get the outcome of your missing variable. Okay, that's what the Pythagorean theorem delivers if it's executed properly. So this goes back to using these conventions. So let's begin by labeling the triangle. Now the side that's across the 90-degree angle, that side is going to be labeled as C. And then the other two sides, it doesn't matter what they are. This one can be A, the other one can be B. So let's go ahead and lay out the skeleton, the general formula, a squared plus b squared equals c squared. And now we're going to apply the substitutions in order to solve for the missing variable. So a, I'm going to replace it by 5. So I get 5 raised to the second power plus, and then b, we will replace it with 12. And we get 12 raised to the second power, which will equal c. And c, I'm going to replace it by x. So we get x to the second power. And now all we have to do is algebra. So let me go ahead and split the equation in order to distinguish the left-hand side and the right-hand side. And in this problem, I'm going to have to evaluate the left-hand side here. And I didn't substitute correctly. We should have a 5 here. So let's go ahead and calculate the left-hand side. So here, 5 to the second power, that's the same thing as 5 times 5. And then we're going to add 12 to the second power, which is the same thing as 12 times 12. And that is going to equal x to the second power. But since we have a variable, I'm not going to expand it. I'm going to leave it as x squared. Now on the left-hand side, 5 times 5, that's the same thing as 25. And we're going to add 12 times 12, which is 144. And that equals x to the second power. And then 25 plus 144 is equal to 169. And we get x to the second power. In order to get rid of this second power, for us to isolate x, we're going to have to apply the square root on both sides. So I take the square root of 169, and just to reiterate, whatever I do to the left-hand side, I have to do it to the right-hand side. And I do the square root of x to the second power. So the square root of 169, you can put that in a calculator. You're going to get 13. And then the square and the square root, these are inverses, so they cancel out. And we get x equal to 13. I just want to point out that if 12 would have been A and if 5 would have been B, we would have gotten the same result. So let me go ahead and kind of just show you the start of this. So let's pretend that I would have called this one A, I would have called this one B. If we would have used Pythagorean theorem, this time the substitution would have been 12 to the second power plus 5 to the second power equals x to the second power. And if you do the algebra, you're going to see that we get exactly the same result. Let's look at another example. So here, again, we have to first label the triangle. So the side that is across the 90-degree angle is going to be labeled as C. And the other two sides, one has to be A, one has to be B. So I'm going to label X as A, and I'm going to label 24 as B. So let me go ahead and brainstorm and map out my general equation. A squared plus B squared equals C squared. That's Pythagorean theorem. Pythagorean theorem. And let's go ahead and apply the correct substitutions. So A, that's going to be X this time. And B, that's going to be 24. C is going to be 25. So we get that x squared plus 24 squared is equal to 25 squared. Let me go ahead and split the equation to distinguish the left-hand side and the right-hand side. And we should immediately see that this problem is going to be just a tiny bit more challenging than the previous one. The reason being is that we're going to have to isolate x by getting rid of this 24 to the second power. A little bit more algebra is required, but it's still manageable. So x squared, that's going to stay as x squared, but 24 to the second power is the same thing as 24 times 24, and then that's going to equal 25 times 25. So we get x squared plus, and then 24 times 24, you can use a calculator to get that result. So we're going to get 576, and then that's going to equal 25 to the times 25, which is 625. So we go ahead and we want to isolate x to the second power, so I'm going to subtract 576 on both sides. So we get x squared plus 0 equals 625 minus 576. Again, if you want, you can use a calculator for that. We're going to get 49. X squared plus 0 is x squared. And then in order to isolate x to the second power, we have to take the square root. But whatever we do on the left-hand side, we're going to have to do it on the right-hand side. So that 49 gets square rooted as well. The square root and the square are inverses, so they cancel out. We get x equal to the square root of 49. And again, feel free to use a calculator if you need it, but the result is going to be 7. Let's take a look at one final example. So this time the triangle is a bit rotated, but we will still apply the same principles and begin by labeling the hypotenuse. And the hypotenuse is the side that is across the 90-degree angle. So that's going to be C. And then your other two parts are going to be the legs. One has to be A, the other one has to be B. It doesn't matter which one's which. So let's go ahead and write the general equation of Pythagorean Theorem, a squared plus b squared equals c squared. And now let's apply the correct substitutions. So a is 3.6 this time. So we get 3.6 to the second power. And we're going to add b. And b is denoted by x this time. So we get x squared equal to c squared, and c is 7.4. 7.4 to the second power. So let's go ahead and split this equation, distinguishing the left from the right. And we have decimals here, so it's actually a good idea to use a calculator here. But let's continue in the meantime. So we're going to get 3.6 times 3.6 plus x to the second power, which is going to equal 7.4 times 7.4. 3.6 times 3.6 is going to be 12.96. Plus x squared, and then 7.4 times 7.4 is going to be 54.76. I'm going to subtract 12.96 because I want to isolate x to the second power. So whatever I do to the left, I have to do it to the right hand side. These ones cancel out. We get 0 plus x to the second power. And then 54.76 minus 12.96 is 41.8. 0 plus x squared is x to the second power. And then we get 41.8. In order for us to get rid of that second power, we have to take the square root. But whatever we do to the left, we have to do it to the right. Square and square root cancel out. So we get x equal to the square root of 41.8. And if you use a calculator, you're going to have to approximate, and rounding to the nearest tenth, we're going to get 6.47. And actually I did a little typo, it's to the nearest hundredth, 6.47.